Hi, I'm very honored to be here today to talk about my research with Jonathan, who's sitting right here. It studies like as the title, it's like the dynamics of verification with searching quality. So the broad settings, like we consider like the traditional, like you can frame it as a moral hazard, depending on like how you form the model. It's like a principal wants to select one and only one project, and the agent probably knows the project quality. I guess here it's like more like adverse selection, but yeah. But like the agent only cares about like the project being selected. However, the principal cares about like the quality of the project. So a natural problem is like, how should the principal select the project? So this problem has already been studied in the setting where like there's transfer between principal and agent. It's like the quote unquote like contract theory. Where the principal can, so basically the idea is like the principal can use transfer to incentivize the agent to tell the principal its private value. However, in this setting, we consider like two variants of the traditional model. The first thing is like the transfer may not be flexible in another sense. And also we equip the principal with a verification device as already been studied in the famous paper by Ben Parasdecker and Lippmann. So it's like the principal can pay, can pay a fixed cost to actually verify the information of the agent. So the principal can like know the agent's information. So here, like we briefly talk about like why we make these two assumptions. So of course, in real world, there are a lot of occasions where transfer is not flexible. For instance, like in academia, right? So think about incentives problem in academia. You cannot just like pay if you publish your top 5, but just give you like some money, right? It's not feasible. Also, like also in traditional settings, there's like no verification device. But now, like in real world, right? It's like we're at the age of big data, so it's like a third party, if they can incur some cost, although maybe very big, probably not that big, but like they can just like know your private information. Of course, like this paper is not about like data privacy or stuff, but it's just to say why like study models with this costly verification can be important in a lot of ways. Of course, in this paper, we will not address like those problems broadly, but we just consider a simple setting where such a single principal and a single agent and how they interact using this costly verification device. So here's the model. So time is discrete. We can talk about like the continuous time analog in the future, but like so here like the project type would make it to be binary. So there's a high type and low type, and the project type can be, it's only like probably observed by the agent. And in each period, like the type follows like a binary distribution. Like it can be high type with probability Q and low type with probability 1 minus Q. And we assume it's like IID across periods. And it's an optimal stopping problem. Like when the allocation occurs, the game will just end. And we equip the principal with a verification device so that in each round, the principal can verify the agent's type at a fixed cost sig greater than 0. So doing so, like the principal can like know the agent's type. And the cost of the agent to provide this information is assume it to be 0. So here's the payoff. So selecting the type theta project gives the principal undiscounted payoff theta, which is like HOL. And the value of the agent to be allocated is normalized to 1, no matter the project's high type or low type. And they share a common discount factor delta. So here's like you can just say it's like the equation. It's like the allocation occurs at time t, and the principal verifies at like some time index t1 to tk. Then the agent's payoff will be delta to the t, which is delta to the t times 1. And the principal's payoff will be delta to the t times theta minus like the cost and weighted by the like probability scaled by the discount penalty delta to the tj. And if allocation never occurs, payoffs are both 0 to principal and agent. So here we have a like assumption that in the first best case, the principal always wants to wait to allocate the high project. It's like if the principal can perfectly observe the type, if like principal, it's optimal for the principal to wait until a high type emerges. So this will be equivalent in mass to this simple condition. And also we cannot assume like whether like L is greater or equal to 0 or less than 0. So this is more like a kind of like a static bias. So you can imagine like in the case if like L is sufficiently low in the static setting, the principal can do two things. It's like I always just give you the good, and I will receive the expectation of which is literally like Q times H minus 1 minus Q times L, or I can always verify you and only allocate the good if you are high quality, right? So if it's like if L is sufficiently low, this will be, you can imagine it's like optimal to always verify you and only allocate when the quality is high. So this is kind of like static bias. However, here we do not make any assumption on whether which is optimal. So the tools to understand this problem is kind of standard in the sense like there's basically you just like we use like a Bellman equation because like we can formulate the problem as like a Bellman equation, and basically you're trying to solve the Bellman equation. So there are some like revelation principal arguments. It's not very standard because it's not like totally private information, because like at some history you may actually know the type, but all the arguments like they will go through. So just like go directly to the kind of like the intermediate results. Like the problem reduces to the principal will choose the probability of verifying a report theta hat. We denote this probability be x theta hat. And also if the report is theta hat and there's no verification, I mean the principal can like randomize like have a probability of verification. So like if the report is theta hat, there's no verification, then the principal will specify an allocation probability B hat theta hat, and a utility promise if there's if like no allocation happens, which is U hat theta hat. And if like the report is theta hat and the verification actually occurs and there's the outcome theta, so the principal needs to specify the allocation probability and the utility promise to the agent in all the 4 cases. Because you can report high type, but you say low type, and you report low type, it's high type. So like the Bellman equation will be formulated using the state variable, which is the utility promise to the agent. Okay, so this is like kind of like standard with the dynamic, it's like dynamic program. Okay. Because like the only thing the utility the principal can give the agent is to allocate the good. So the state variable will be ranged from 0 to 1 because like the maximum utility is 1. Okay, so clearly like there seems to be a lot of variables, but using like some intuitions we can like get rid of not most of them, but some of them. So basically it is easy to say if the agent is lying and it's verified to be lying, then like the principal should just like burn the project and never allocate to the agent, because the principal has a commitment, and this is a maximum punishment the principal can do to the agent. So basically it's here like it's like you report your low type, but you're actually defined to be high type. And if you report your high type and actually defined to be low type, then like the principal can just like give you the maximum punishment, which doesn't change anything utility unpassed, but just like give you to like make the incentive compatible constraint there to satisfy. And also a second observation is like if you report your high type, I will just give you promise 0 utility in the future. This is also very intuitive because mathematically, if you think about the value function, the only thing, the derivative is bounded by h, right? Because like if I give you one more probability to allocate the good, like my utility can only increase by a scale of h. So basically here's like I would rather just increase the allocation probability today rather than just promise you future utility. And also the third simplification is like if you report your high type and I actually find your high type, I will just allocate it good. I mean that's very intuitive to be optimal. And also if you're reporting your low type, then I will not verify you, right? Because like there's no reason to verify a low type because it's like the low type, right? So after these simplifications, we can actually have a simpler like Bellman equation. So basically, the equation 1 is just like the objective of the principle, and subject to the low type IC constraint and the promise keeping constraint. So basically, because the high type will not bind, so we only need to keep track of the low type IC constraint. Okay, so now we can go directly. So basically, the left is just to solve this Bellman equation. So we can go directly to the solution. So like basically there are 3 cases. So the first case is when the cost of verification is less than the high type quality, and the infinite is like taken to be sorry, the horizon is infinite. So then in this case, the optimal maximum we call it increasing chance maximum. So basically it has certain features. So basically the allocation only follows reports of H for the first T star -1 periods. Okay, so basically there will be an endogenous line even if your horizon is infinite. So the feature is like every period you will report whether you're high type or low type. So if you are high type, I will verify you with a certain probability. If you're low type, we'll go to the next period. And when it hits the deadline T star, no matter what type you receive, I will just give you the object. So of course, in each period, like when you report your high type, I will verify you with a certain probability, but the probability will decrease over time. And in the final period, because I will always give you the project, the probability of verification can be seen as 0. And also, like if there's no verification happening, or like I verify you're telling to choose your high type, I will just give you the project. And if you are verified to be lying, I will just burn the project. And yeah, and that's what we already said. So basically, the intuition here is simple in a way, like because the only way to keep the low type telling the truth is to promise more utility in the future. So like the utility will increase, like the reservation utility will increase in the future, but because your reservation utility increases, so I can verify you with less probability, because it's more costly for you to lie. So this we feature as a increasing trust mechanism, and also because your utility is bounded by 1, because the most thing you can say is to get the object. So like the finite horizon is expected because I cannot promise you more stuff. So this is one instance. Okay, so seems like already like some of the details here. Yeah, so basically, yeah, we can just skip it. And another case we consider is like the decreasing trust mechanism. So okay, it's not we consider, it's like some feature. Okay, so if like cost is less than a high type quality, but if you are not given a sufficiently long horizon, like your horizon is like smaller than some threshold, which depends on the factors of the model, then the optimal mechanism will have this following feature. It's that in each period, I will verify you with a probability, but like the verification probability will actually increase increase like run by run, and in the last period I will always verify with probability 1. So basically this is like also the intuition is like when you are thinking about the value function, like the original increasing trust mechanism is like you're going to the right. So like the reservation utility is like increasing, but here it's like you're going to the left. So like the reservation utility is decreasing period by period. And so that's why you have to verify with more probability each round. And in the last round, you will verify with probability 1, and which corresponds to the least reservation utility. So this can happen if your horizon is not very long enough. So the reason is like because you do not have, when you want to use your verification device to give incentives, you need a sufficiently long horizon to make that happen. If your horizon is not long, then you cannot fully like utilize your verification device. So instead, you will use like a decreasing trust mechanism to actually be your optimal mechanism.
And delta mechanism.
Oh yes, and L is negative. Right. But if L is not negative, like this T bar may not be defined because this T bar is so implicitly L is negative. So like the punchline here is like you need for the verification device. If you want to use it to overcome the static bias, you better have like a long horizon. And also we talk about the case when like C is greater than H. So if you think about like C greater than H, intuitively seems like verification may not be useful because for any probability you're verified, you can get at most H, but you have to pay a cost C. You have to get it. But however, this is not the case because if you think about like verification, although if you have one more probability to allocate to the high type, you pay a cost C greater than H. But this will actually increase the reservation utility of the agent, so which makes you easier to make your incentive compatibility constraint to hold. So this is kind of like sacrifice the value of allocation, but just to make you easy to screen the agent. So in this case, we say it's greater than H. The optimal maximum will be like a randomization phase and a verification phase. So basically, in the randomization phase, you are just like burning the project because like the cost of verification is so high. So you need to allocate with the probability strictly less than 1 to make the agent incentive compatible. And then you start to use like the optimal verification maximum as we shown before. Okay, so here's like the continuous time analog. It's a continuous analog. So basically, we can change the model to a Poisson model. In a case like if you think about like in each period, like you feel like time horizon is like delta, 2 delta, 3 delta, and you like make the probability to be Q delta, and you take delta goes to infinity, it will be a Poisson model, which is kind of like in some bargaining model, probably there's some feature of it, right? So it's like, but here is like the 3 plots in the continuous time. So the first part is like the verification probability of like the increasing trust maximum. You can see it's like goes to 0, and the second would be the decreasing trust maximum, like it goes to 1, and the third will be the when the maximum like when the cost is very high, so you have to first randomize here. It's like you do not use verification, but your allocation probability is not 1. But then at some point it jumps discontinuously, like you have like always allocated with probability 1, but you start to verify, and in the end you're just always allocated. Okay, so here are some like literatures. Okay, the time is it's there, so it's just like skip it. So you can find in your paper. We actually do the literature. Yes. All right. So thank you. And if you are, so basically we are just one more point. It's like we basically want to do something more general, like using like to think about cases where in dynamic setting where people have like hard information, but like they do not have transfer. So like this model is very simple, but there are a lot of ways we can make it like more complex and study more important. I mean, this is also important, like other important economic applications. All right, thank you so much.